And we are online. Okay, let me check if switching slides works. Okay, so a few years ago, way before my golden Rust times, I was working for a certain company that was using a time tracking software. So this particular software, it took a few screenshots each hour, screenshot every few minutes. And there was only one issue, and the issue was that if you haven't worked in the time between the screenshot, and for working what counted was moving your mouse, touching your keyboard, whatever. If you didn't do that for a few minutes, this particular 10 minutes or 20 minutes, how long you happen not to touch your keyboard, it was not counted towards your time. So this might seem like fair system, but if you have to go to the toilet, you usually just ask the person sitting next to you, press Control a few times when I'm gone. Around that time, I already kind of sort of knew what microcontrollers were, and I decided that this feels like an engineering problem to solve. So I knew I couldn't have done it through software because someone before my time at that company already had tried to do it, and the company had issues because of it. So I took a bit different approach. I built a device that fakes being a keyboard. So that's how the device looks like. Could you maybe post the feed from the camera here? Oh, so that's the device. So this is a USB device. It's got some, transistors, some LED, and this chip in here. And when you plug in this device to your machine, it will identify itself as a keyboard. Actually, it will say, in hindsight, I shouldn't have really done it this way, but if you plug it, it will say that this device has been made by Wychowaniec, so me, and it will identify itself as keyboard cheater. So in hindsight, I could just call it, ergodox, but well, and all this device does is, like I said, it identifies itself as a keyboard, and then it waits a few seconds or so, and then fakes pressing Control or Shift or Alt. And this way, if I had to be off for a while, I just plugged in this device, went to the toilet or whatever, I don't know, go dance for 2 hours, then went back and plugged it out, and everything was fine and dandy. And could we go back to this? And that's how my great journey with AVR started, and that's how I'd like to welcome you to this talk on microdosing Rust, on how and why and how to get started with AVR. So a little bit about me. I've been coding in Rust for a few years now. I'm Rust and a Nix apostle. Nix is technology for building programs. So it's like, make files but on steroids. I won't be discussing Nix in this presentation, so no worries. I'm currently working in travel industry. I'm writing Rust for NXA, doing also some open source contributions, and I've got a blog. So if you like a little bit about Rust, I've got a fantastic series I wrote last year about genetic algorithms and neural networks. So creating one from scratch entirely. If you don't know what they are, or you would like to refresh your knowledge, I highly encourage you to take a look. Okay, so a little bit about us. So over the next 40 minutes, I'm going to introduce you to what AVRs and microcontrollers in general are. We'll take a look at why and when it makes sense to use them. And finally, there's going to be some live coding on how to use them. For this live coding, I have some stuff prepared on the table. I will not attach all of them because this would take too long. I have a few prepared. So, what are microcontrollers? Well, in general, those are microcontrollers, somewhat obviously. For instance, what characterizes them is you could treat them as sort of tiny computers, basically. It's a bit of too much, but basically if you treat them as a lower version of a computer, you'll be fine. And to give you a sense of scale, because well, you might see it on the camera or in here, they're pretty tiny. The smallest one that I keep in my hand is the one on the right side. Then we have, actually the one in the middle is the most popular one, and some bigger one on the left side. And to give you a sense of scale, here's, potato. And because I know a little bit about statistics, and I know there's different kinds of potatoes, here's a potato to scale to that potato, which if you assume that I took out at random from the store, you can get this sense of scale that they are tiny compared to this, whole machine I have on my table. And the microcontroller in the middle is probably the most popular AVR, so that's called Atmega 328P. If you Google for, Arduino, Uno, or whatever, this is the Atmega that is put in the Arduino Uno. And if we zoom in a little bit, that's how it looks like. So I said they are kinda like mini computers, so maybe let's compare them to a computer. So for instance, this little boy, and to show you that's how it looks like in real life, this little boy can be clocked at various frequencies. Usually you will get around 16 megahertz. So this in practice means it can do 1 addition per one clock, so about 16 million additions per second. So that, is it much? I can do maybe 6 per second, so 60 million feels like a match. So maybe to compare it with some actual machine, and the machine I was creating this presentation on was using Core i7. It's got 12 cores, where each core can be clocked at stable 2.2 gigahertz, and let's do times 1000 to have megahertz on both sides. So for comparison, this little boy has 16, and the machine that this presentation was being developed on has around 26,000. So if we divide both numbers, we will see that, this Core i7 is around 1,006 times faster. This is not really accurate because, those modern CPUs are very complicated machines. You have this super scalar stuff. They can execute, 1,000-bit operations, whatever. But this should give you a bit of scale. So if the AVR is not a master of speed, then how about, RAM maybe? Usually, I guess, typical nowadays computers have around between, 8 and 28 RAM, more or less, gigabytes. And in comparison, this little guy has 2 kilobytes. The smallest AVR has 512 bytes. So if you were to generate, put an HTML server there, you would be able to generate at most 2 kilobytes worth of HTML at once. So it doesn't feel like much. And they are also similar to typical computers if you regard the storage, because usually when you write a program, you store it on the HDD or NVMe or SSD. And Atmegas also have built-in memory. They don't have spinning disks or NVMe. It's not that fast, but they have flash memory, the same you would have in your phones, I guess. And for comparison, this little guy has 32 kilobytes of flash memory. That's 32,000 bytes. Don't know how to compare it because usually that's not 32,000 of Rust characters because you compile it down to binary. But I guess something up to, if you were to, for instance, embed some string messages in there, then some hello world message takes around 15 bytes. So this can quickly add up. But as we'll later see, even though this 32 kilobytes kind of feels limiting, this is really a lot if you know how to program for those kind of things.
To the compare, LS binary has 130,000 bytes.
Executables can get a bit of large. So I started by saying that they are similar to computers, smaller. So why would you use this kind of thingy when you have your computer, which is faster, has more memory, has more flash, has more everything? It's connected to the internet. And the reason why you might use an Atmega such as this one is visible on this very presentation, because those are those boys called pins. I only highlighted 4. In reality, most of them are usable. And the difference between when you write a program for a machine like typical PC and let's call it machine and machines such as this AVR, is that your program on AVR or any other microcontroller has full control over the CPU. So your program can turn off and turn on those pins. So for instance, I have this hefty big machine in front of me, and I have this little, maybe I'll show it in here too, I have this little LED. Yep. We are on different frequencies. Yeah, so I have this LED, and with this hefty machine in front of me, how do I make it flash this LED? I want to make it blink every second. I can try to plug it into a LAN port. Oh god, I can plug into USB and I'm out of USBs because they break. I could do it through audio jack, but I won't. And I guess that's it, because I have just Thunderbolt pin, which is even worse right here. If you had some older PC from like 20 years ago or more, you could kind of sort of hack it through serial port or LPT port with some transistors and stuff. But with just laptop, you are not able to do anything meaningful with this LED. And this is in comparison with just Atmega, because if you want to blink or just communicate with some any external device with Atmegas, you just attach this LED pins to one of the pins of the Atmega, another one to the power source or the ground, depending how you wire it, and it works. And this was for the introduction. Now, to actually prove that I know what I'm talking about, what I'm going to do is actually make this LED blink, and then I have some other stuff that we're going to connect. And I'm going to show you how to do it in Rust. If you are proficient in Rust, you will see that the programs we'll write will be a bit different than typical Rust code. Not much, a bit. If you are not proficient in Rust, you won't recognize the difference. So, okay, and let me switch to my editor. Okay, so that's not my editor, that's Firefox with some plugin. What I wanted to do is, I want to avoid writing random comments from, out of my memory. Not because I can't remember them, but it's hard, but because I want to show you that it's actually simple and the commands are not random. So what I'm going to do is to Google for Rust, and the crate for AVR I'm using. It has examples and stuff. So I'll just show you. I'll go through readme, copy, paste comments and end up with working code. So there are some crates for Rust you would like that are available. The one I'm using is called, it's a bit unfortunate, I cannot scale up those, but if I open, if Google with results open up, you will see the name. It's called, trouble finding that site. Okay, it's called AVR HAL, which stands for AVR Hardware Abstraction Layer. If you have different kind of microcontroller, you would go with, I don't know, your microcontroller kind HAL, you probably find something. So that's the crate I like, and there is separate repository with templates. bit awkward because, again, I'm using Linux, so I cannot have screen mirrored, so I have to look that way. And we have cargo template for AVR HL projects. Let me zoom in back again. And I'm kind of prepared because to actually use this, you have to have cargo generate installed. I've done it before. And this application called RaveDude is used to actually upload the code from your computer to the AVR. I've already also installed it. If you were starting, you would just do those. And then this thingy basically clones this repository locally. And this repository contains some pre-filled cargo dependencies for AVR projects, some hello world template that blinks the LED. So I'm going to do just that. Okay. Generate. And one thing before we continue, because I've been talking about AVRs as freestanding devices. It is possible to flash them when they are freestanding like that. I usually do it, well, not usually, but for the purposes of this presentation, I'm going to use Arduino. So Arduino, if you don't know, Arduino is like a wrapper for this AVR, because I have this AVR inside, so this is pluggable. Let me show it also here. And then what Arduino provides is, USB port, so that I can easily connect it, and also provides this pinout, so it's easier to attach cables to it. And thanks. Okay, so our project name will be just demo, and then this particular template supports a few different Arduinos. Most of them are based on AVRs, and the Arduino I have is Arduino Uno, so that's just that. The project is set up. Now let me open it in the editor. I will zoom in a second. Okay, so this is the source code that Cargo generated for us. Some license, some README, some Rust code chain, and the only file we're interested in really is main.rs in here. Okay, so again, let me zoom in, let me delete this comment so that more code is visible on the screen. Okay, and this is the Rust code for the, at this point you could call it Rust firmware. If you wrote a bit of Rust, you will see that some things are different. So we, for instance, have no std, which basically means you cannot, say, create strings or vectors with dynamic sizes. Mostly because if this AVR has only 2 kilobytes of memory, then keeping track for the memory allocator which regions of the memory are free would take additional space out of that RAM. That doesn't mean you cannot use most of the Rust features, so you are free to use, traits, references, anything, just not, stuff from std such as vectors or file system, because there is no file system in here. Then we have a bit different main definition. You will see it returns bang, so this exclamation mark operator. This basically means that our main cannot stop working, because when you have typical program, when your main stops working, you are back in your terminal and the window closes. But with microcontrollers, there is no defined condition what should happen if your program finishes. So usually if your program just does one thing, then you just loop it forever. And in this case, what the program does is, this is some initialization stuff. It prepares the CPU. Then we'll see that it takes some pin, marks them as output pin, because pin can be input when it's supposed to accept some information from the outside, or output when it's supposed to go high and low as you wish. And then we have just this simple loop that toggles the pin high and low each second. So from Rusty language to real life usage, what this does is that it flashes the LED, waits a second, also turns up the LED, waits a second, turns off the LED and stuff. And to flash it, I will also open the terminal right here. Zoom in a bit. Flash it with the template. I've cloned it. The flashing really boils down to running cargo run. Some Rust programmers might not be aware of why this will work instead of running the code locally. Because in cargo tom you can specify different comment what should happen when you run cargo run. In this case, the template we are using just aliases cargo run as cargo flash to this AVR, so that it's easier to use. So in reality, what this cargo run will do is that it will compile the code in Rust, link it so that it's ready for AVR, and send it through this USB cable onto the board. I know for sure that when I click enter it will fail, and that's deliberate, because I want to also show you the dependencies that you will need if you want to play a bit. So they are basically, apart from the two cargo installs that were in the README, there are two additional dependencies. They are also mentioned, but just to show you, the potential error messages you might see. You might see a message that says this one. It means that you are just missing, you are missing what this says, you are missing linker, because it's not usually installed on typical systems since most people don't do AVR. In my case, installing it will be easy because I will just do packages cross, and GCC. If you are on Ubuntu or a macOS, you will just Google for Ubuntu AVR GCC, macOS AVR GCC. It usually boils down to a single command. Okay. Now if I run cargo run again, it will fail once again on a different dependency. The dependency we are missing right now is the actual program that takes, in this case, Rust compiled binary and flashes it into the Atmega. So again, if you were on Ubuntu, you would Google for Ubuntu AVR Dude. In my case, AVR Dude. I will do cargo run. And could we have a stream to?
Yes.
Oh. Once again, I saw it error out. No matching serial. Probably I have to disconnect it to match it. Okay, let's try one again. My cable is a bit flaky. That's not it, so. Oh yeah, now it's just my cable being flaky. Let me try connect it again. Okay, now I see it being detected. Okay, once again, cargo run. You see it's being programmed, and when it finishes, then why I've been rehearsing this if it still fails on me? Okay, yeah, so this is just my cable being flaky. So I don't actually have attached the LED yet. That's because the Arduino board, maybe I'll try to somehow set it up. The Arduino board already has one LED, at least one LED built in. It's connected to the same port. But if I wanted, I could just as well go ahead, connect this little guy. If you have friends that are engineers, they will tell you not to do it because you will fry your CPU. Obviously, in this case it works because I will just disconnect it easily right now. If I left it running for longer, it might break the CPU because in reality you will need at least one transistor, some resistors, blah blah blah. It worked, so don't do it at home, but don't tell anybody. And blinking stuff is not the only thing you can do with Arduino, or at least with AVR Rust. Because in normal applications you can also do such stuff such as print link, so you can print stuff. There is a similar way you can do it for AVR, because what this cable provides is not only connection to flash the board, it's also connection to the UART of the AVR. And UART is like a serial console provided by the CPU. So what we can do is the CPU can execute instructions that will send text and can receive text from and to a computer. And it's very easy to set up. It's not println, a bit unfortunately, because, for instance, some AVRs have multiple UARTs, so this wouldn't know through which UART to send it. But it's very easy to set up. And once again, not to write random code out of my mind, I will just go to examples. If I manage to open back. Okay, so we are back. So this was AVR HIL template, and the main crate is just AVR HIL. It contains a special directory of examples. Those are examples for Arduino Uno, and there is one example with sending stuff through UART. So I'll just copy paste basically not the whole example, because this example also does reading from UART, but to make the demo simpler, I will just take the example that sends stuff from Atmega to my computer. So those two lines. Okay, and well, let's replace the LED logic. Can I make the wrap lines? No, with wrap lines as well. Okay, so maybe like that. Yeah, this should do it. Okay, so the code we have now, what it does is that initializes the serial console. So then the serial object we have will allow us to send and receive text. The variables here are, those two from initialization stuff, and this third integer tells the speed of the UART. So we'll stick with the defaults, but just if you're curious what this integer means, it's about the, bits per second, how fast you want to travel through UART. Because I think there is no negotiation algorithm, so if you want to connect two devices through this UART protocol, they have to agree on the speed. So in this case, I know it's hard-coded on my computer side to be this 57,600. If I changed it, I would also need to change it in my computer's template. So we'll stick with the default. And you will see that sending stuff is actually very similar to this print link. We're using different crate. There's a special crate for sending those strings. Then we have to paste and use the variable, and then just the string we want to send. This operation cannot fail in theory. So how about just something like that to silence the warning? Then do it at home. And then if we do cargo run, and if my cable is still working, and I think it is, what we will see is hello from Arduino. And to make it more interesting, we can obviously, for instance, use, what can we use? Counter. Because through this write-on, you can use not only static strings, but also can use regular formatting. So we can do something like i+1, and then in here we can say, and write this.
Can you write Whatman?
Whatman.
Do you remember this video?
From JavaScript?
Yep.
Yeah, I remember it was. Why not? Okay. So everything should work correctly. Now each second we will see a new line appearing. Okay, so that works. That works if we want it. As I said, UART is like bidirectional, so you can not only send stuff from Atmega to in this case my machine, but in theory every other machine that supports UART. You could also read stuff. And changing subject a bit. Does anyone know what kind of bat that is? There are some wrong answers. I had to ask my girlfriend. Okay, so fortunately I don't have candies to give up, so no one lost really anything. But this is called, in Polish this is nocek netetera, in English something like netetersbat, I guess. And I had the opportunity to, first of all, they are protected in Poland. They are under strict, I don't know if it's called strict protection, but in most cases you cannot really go as close to them as I went. But I had this special opportunity around a year and a half ago to go with a group of people who study bats, and we went just to count them around an hour from Wrocław. And that's when I took this picture, and I wanted to mention it because I do have one device that works like a bat, so to also show it on the camera. Yeah, just so that I know it's in focus. Okay, so what this device does is that it's got, two pins are for the power, and then if you send some signal on the first pin, it sends sound wave, which then goes back to you or not. And then on the fourth pin, you get the answer how long it took for the sound wave to go back. So what this basically does, it's that it measures the distance from the device to the nearest wall, or the object itself, up to 3 meters or so, I think. And what I'm going to do now to show you that writing Rust for AVR is easy is that I'm going to connect this device to Rust. I will program it, and our program, after we finish, will just display constantly after each second distance to the nearest object from this device. You might easily imagine doing custom Roomba with it if you make like 8 of them or something. In our case, we'll just send it to the nearest wall. And what I'm doing is that, as I said, it's got 4 pins, so 2 are for power. So I've got 5 volts in here. I've got the ground. Let's keep it in here. And 2 volts we can attach, basically anywhere, because we can program most of the pins. So I think those 2 are convenient. Okay, yeah, let's leave it there. Could you open the code back again? Well, opening code will be up to me. Okay, so we are back in the code, and how to start from now. So first we'll need access to 2 pins, because one pin is the pin that will set to high to notify the device that we want for it to start measuring, and the second pin will be answer from the device. So I will just copy paste the names as I have written them on the board. So I see one is called trig, the second one is called echo, and trig is the one that we will from our Rust code send to high. So this will be output pin, and I see I've got it connected through here. On the side it says 8, so this is pin called D8, just the 8 and into output. Then the second one is D9 because it's near to it. Yep, D9, and the other one is just input, so into input. And according to the specification for this particular device, what we need to do for it to start measuring is to set trig to high. So basically, send 1 there. Then we have to wait 10 nanoseconds, microseconds. Yeah. And then we have to bring the pin low. So this will trigger the device to start measuring. And from the device point of view, what it does is that the echo pin will be low for a while, so it will say 0, because this is the time where the device is measuring. So we have to wait until as long as this echo pin is low. So this is the time the sound wave traverses and has to go back. And the way the device sends us the information how long was the nearest object is that it takes the echo pin high for some time, and this time tells us how far this object is. So basically, first we wait until echo starts to be high. So conversely, we wait for as long as it's low. Now echo is high, and we have to measure for how long echo is high. And according to the specification of this device, we have to wait one microsecond. Then we can print this as a distance. And we should be set. And then we wait 1 second for another measurement. Okay, so maybe let me try to open the terminal. Back again. Okay, I see the cable is still online. So what we should see now, after we flash it. Alright, I forgot to make one variable mutable, because obviously the set high and set low, they modify the state, so they require for the pin to be mute. Also, just to give you an example of neatly designed API, when you write similar code in C, you don't really know which pin was set to high or low. You have to somehow assume the other function does it neatly. With Rust, they use type state pattern. So if I expanded the type hint underneath, we will see that, for instance, this strip is of type pin. This pin has two generic variables. The first tells it what's the spin mode. Is it output? Is it input? If it's input, there are, I guess, 3 different kinds of inputs even. And then this PB0 and PB1 are the aliases for D8 and D9. So I was just wanted to show it as an example of a neatly designed API, because with this API, you cannot accidentally do something like echo set high, simply because there is no such function on pin for input. Okay, so we've got this whole stuff. This waits for a while for the device to know that we want to take measurement. Then this is the time device takes this measurement. The output goes high, and we measure how long it takes for the output to get low. Okay, we've got something. Okay, some bigger variables. Ideally, if I now put my hand, some number. If I move the hand further away, the number gets bigger. So okay, this seems to work. Obviously, those are not centimeters, but I never said they would be. So maybe let's make them centimeters to make it more understandable. And once again, this is kind of a magic constant, but this is because that's how this manufacturer built this device. The manufacturer says that for each microsecond, the echo pin is high. We should measure 58 millimeters. Snap. We just have to divide this by 58. This will work. Because that's what the spec says. This should give us centimeters. So why don't I jump to the end of the string and also write centimeters in here. By the way, this \r is just a way to say a new line. So without this r, all the messages would be just in one line.
And why not /n?
Yeah, so this goes back to 80s. Because you already see that this is Wrocław, ln. So ln stands for line new,
Okay.
Pascal convention, I guess. And what you need to actually send a new line in devices that simulate terminal emulators is both the new line character and one character that says go back to the beginning of the line. So this ln, if we were to, from the terminal's perspective, what it receives is that some text. It moves the cursor. Then it receives /n, so move to new line. It moves to new line.
Okay.
It starts, from the previous x coordinate. So
Like Windows.
yeah, like Windows. So that's why we need this \r. It's not actually new line. It's carriage return. That's why it stands for R. So if you were to open a terminal emulator without /r, you see distance something, it will swim away from you. Okay. this one, and right now I think it overflow. Okay, so in this case, this is somehow, I guess, between 10 centimeters. There is some margin for error, obviously, because this is not production ready. But generally, we see that when I move my hand away from it, the distance increases. I guess this is 20 centimeters. What it says, 130, something like that. Well, it works. So, and I don't have to present it to the client, so I know from my perspective that it works. And as far as the demo goes, I just have a few more examples, but they are just videos. And and I will show them to you in a second. But I wanted to talk about various different accessories you can use to communicate with your Atmega. So obviously there are some, just to show it on the camera, there are some biggie screen boys. And this is from an old Nokia, this old Nokia screen. You can also very easily, this is a very popular screen as it turns out. You can just communicate from your Rust code to this processor. There are some LED matrices. So this is basically like a screen but with just binary. I guess it's red. There are SD card modules. So what this does is, as I said at the beginning that you have only 32 kilobytes of flash, but you can always just stuff rest on the SD card and make your program load stuff from that SD card. So really sky's the limit. And to show you some examples of more interesting stuff that I wouldn't be able to live code, I wanted to show you 2 videos of stuff I've done in the past on AVRs that I think are interesting. So if you could go back. Let me just navigate to the video.
By the way, what ID do you use?
That's Emacs.
Okay.
You don't have to use Emacs to code for AVR. It doesn't help. Doesn't make it worse though too. Switched like a year ago from IntelliJ. If anyone wants to try, this is Doom Emacs. When it comes to Emacs distributions, it's pretty popular, so I would recommend it. It works great with Rust Analyzer. And I have the video stashed in some directory.
So we shouldn't ask your opinion about Vim.
Sorry?
We shouldn't ask your opinion about Vim.
No, you should not. You should leave. No, but please don't.
Actually, Emacs has Vim bindings.
Yeah, I do have Vim key bindings, yeah. Okay, so I have 2 demos. One is a game, and I guess I have to move it to screen first. Okay. This is a very old video from 2015, so, but it uses AVR. It uses AVR, this is what we call AVR on a breadboard setup. So you will see that there is no Arduino. This is pure AVR, some cables, some transistors, and, well, it's in Polish, so it says score, and then best is not in Polish anymore, so it's best. And then you have 3 buttons. I guess there's 4th also, which is, to reset. And you basically control the snake, so. Ta-da. So I would say it's not much. I would say it's an honest work. I had a blast writing it. It's not in Rust, because as I said, it's from 7 years ago, 2015, I guess. So it was written in C.
Okay.
But I wanted to show you because it's still AVR. I had a blast writing it, so yeah, and the stress of the connection. So you will see it's not even connected through USB. It's just battery from my old dead phone. Because why not? And before someone finds it out, I will just shut it. And I have second one, which is a bit different. This is even a different kind of project. So it also happens to be using AVR, well, obviously, and it happens to be using this same screen from the Nokia. But this is a bit different project because maybe some of you know what a bad app Apple is. This is like, I didn't know up until some time, but I went on a contest with a friend because he showed it to me. And Bad Apple is like this 5-minute, I guess, YouTube video in grayscale of some anime girl dancing or something. It's like some anime stuff, and there is it's garbled. There's unspoken contest to either display it on some different devices, say your refrigerator, because the same you'd run done on a refrigerator, but because this is video, well, no, not this video, I'll just wait a minute until I focus. Okay. But because this is video, it's a bit different because you have to think about compression. So first, I let it play it.
So are you like streaming this through the PC to the microcontroller, or is it like stored locally?
Oh yeah, so it's stored on the microcontroller. So that's why I started with saying that it's a bit different, because you have only 32 kilobytes on the AVR, and then the problem is, the whole video, if you just download it from YouTube with the whole resolution and stuff, would take probably, I guess, 100 megabytes or so. And then you have this AVR with 32 kilobytes, and you have to store that both. I mean, you don't have to because no one forces you with a gun, but if you want to, you can store. Well, first you have to take some place for the encoder itself, because you have 32 kilobytes both for the data and for the video itself. So there is this trade-off between how good encoder you can make and how much place encode it takes. Because if your pure code, not counting the data, takes 30 kilobytes of code, then you have only 2 kilobytes left for the data itself. And the other way around, if you have a simple encoder, then it probably doesn't. The decoder probably isn't that good, and you will see that the video cuts after a few seconds. That's because I did not manage to put the entire Bad Apple there. I've managed to I guess it was like 20 seconds, and it was not. It was a bit of cheating because I was skipping frames.
Okay.
Because the thing I used for that is just basic run length encoding and some other video hacks I found. So basically, if have whole black line, then I don't store. The resolution of this boy is 84 by 48. So 84 times 48 times divided by 8. So, because it's black and white. This will give us 504 bytes per each frame. So with 500 bytes per frame, you would be able to store in this 32 kilobytes, I guess around 60 frames with your code here. So then you'll have to get somehow creative with compressing this stuff to just even make it fit. And as far as demos goes, that would be it. I have some other devices, some more screens, but that just to show up and maybe encourage somebody to try. If say in this one, if you want to you shouldn't make your own cryptography, and you shouldn't make this your door lock, but if you want it, no one's stopping you, so I would just suggest it. And let me go back. Just to sum up this all stuff I've been talking about, where do we go from here? So if you don't know microcontrollers, or you don't know AVR, you surely didn't remember how to code it from scratch with just this presentation. That was also not the point, because there are lots of great tutorials online. So if you become interested for microcontrollers, I would encourage you to search, for instance, first of all, unless you are really into electronics and stuff, do not try to just buy random microcontroller and try to program it, because this might be frustrating. So what I would suggest, if you want to start, is to buy an Arduino, such as this one. It's a bit pricey now because I saw it for like brand new, go for like 90 zlotys now. You might probably find something cheaper on OLX or something. And with just Arduino, it's also not very fun because you have one LED that you can blink, but we already saw how the blinking LED looks like, so it's not really fun. But what I'm aiming at is that there are some kits online, or sets of stuff online that are composed by people who are interested in electronics. So if you Google, for instance, for Arduino basic kit, whatever, you will be able to buy the whole kit with like cables and stuff, and some displays and some monitors, not monitors, some
Screens?
sorry,
Screens?
czujniki. Sensors, yeah, with some screens and sensors and stuff. And if you wanted to try, I would encourage you to call, Arduino kit or whatever. The store I like, and this is not an advertisement, but I very like Botland. They are Polish store, so if you go for Arduino, Zestaw, Botland, you will find it.
Botland?
Botland.
Okay.
Yeah, like bot and land. Very helpful indeed. If you want, obviously you can do everything by hand. So for instance, I was showing you this device previously, this keyboard cheater. So this was not built on an Arduino. What I've done is that I basically bought, and this is not a PCB you would normally do in home, because there are different ways to do PCBs, with traces and stuff. But you have to have some acid chemicals and stuff for that. So what I do instead, because I have dogs and I'm afraid they would lick the acid, or I would lick it, is that I buy just PCBs with size which I more or less anticipate, and then I guess you might not see it from here, maybe you will see it on the camera, but those are not traces, those are in this case like the legs of the transistors that I don't really use anymore. So what I do is that I plan the PCB on either in KiCad or on a piece of paper, and then I will just connect all the pieces with using broken transistor legs. So this is very cheap, very nice way. Encourage it. And as far as the programming languages go, Rust is pretty nice target. The AVR is kind of in its early stages for Rust. So while I would encourage you to at least try it, if you want to do something more a bit complex, it would be not impartial for me to mention that there are better architectures such as AVRs, such as ARMs, for which you will find much more resources. I will show you AVR because I very like this architecture. It's simple and I've been playing with it since forever. So obviously I'm biased towards AVR. But if you just Google Rust microcontroller, Rust microcontroller board, you will find lots of them. And as my last slide before we go to some possible questions and stuff, or you know what? No, let's do questions first because the last slide is a bit of a killer. So, do you maybe have any questions about whatever presentation? AVRs? Yeah. Oh, sorry. Yeah.
It's possible to use standard Arduino libraries?
Oh, that's a good question. I didn't mention. In theory, yeah, because those libraries compile to the same AVR binary underneath, but you would have to use, you would have to prepare bindings on the Rust side. I haven't done it for AVR. It is in theory doable, but yeah, you might be, unless you really know what you're doing, you might be better off rewriting the code and then submitting to the original repository and getting rid of the C version. But yeah, so in theory it should be doable. I wouldn't really recommend it because it might be tedious and time-wise effort. It might be simpler to just, looking at the C code and doing similar stuff in Rust. Yeah?
So you mentioned there's like a lot of those peripherals, components you can plug in, and well, you've done some live coding, and it was like pretty simple to set up this distance meter, but the different ones, like the screens, seem more complicated. Are there like Rust crates for them, or do you code?
Yeah, for some there are Rust crates. For instance, this screen, as I said, is pretty popular. So, screen from old Nokia. I forgot the model name, but if you Google for Nokia 5510 screen, whatever, you'll find it. And I think there are some libraries in Rust. So all you have, obviously, there are more for C and C++ because it's just longer living target. But there are some crates.
Is it like how dependent? So
it depends on the crate because there's a bit of a history in the Rust AVR target. So it was basically dead up until 2 months ago when I fixed it because I needed it for my project. So for about a year and a half, the Rust compiler wasn't able to compile for AVR. It just stopped working at one point, and nobody had time to fix it. Up until just 2 months ago. So lots of crates that used to be working, they are now not working because the compiler got upgraded in the meantime, or people abandoned them. I see the ecosystem is now proliferating once again. So hopefully after a while we'll be able to rewrite everything in Rust. Obviously, what I can say. And you were mentioning about some peripherals, and I also have one more example I forgot that I will show in a minute, a bit more also live, but not with live coding. But before, I also saw somebody else had a question, yeah?
So I wanted to ask, because I tried like doing stuff with Arduino and Rust before, and I got stuck on trying to read an analog pin. Because in the C framework, you can just call analog read. There is no such equivalent.
Yeah, there is. So actually with this AVR HIL, what you will do, and I don't want to waste time coding it, but it's very simple. You would do pins.pinname.into analog, and then there on this analog pin input you have just like a read or get reading, something like that, and you get the raw U16 value. So I would guess it's even a bit simpler than the equivalent C code, because actually the ADC, so this analog converter on AVR is asynchronous. Not asynchronous as in Rust async, but when you start measuring stuff, it takes a while for it to finish. And doing this in C is a bit awkward because you have to set the controller to this measuring mode and wait up until it controls the CPU tells you I'm ready, and then read the value. And in Rust code, you just call into analog, and then on the pin you'll have just get reading or something like that. Yeah, I saw also. Yep.
Yeah, just a curiosity. This Rust compiled code for AVR compared to the C compiled one, in size will be equal or smaller, bigger?
Oh, so actually those are two different compilers underneath, because Rust uses this LLVM project stuff, and for C you would use AVR GCC, so G++. I think G++ generates better code, especially around some operations such as division or multiplication. I haven't had any particular issues with the LLVM one, although I don't really have much of a comparison beyond, the GCC is a bit older, so it's probably a bit better. But if you'll see at the LLVM repository, there's lots of committed to the AVR target, so hopefully it will get better over time. Yeah?
Yeah, I wanted to ask about the AVR fork, but you already mentioned it got fixed. So I have a question that in Rust there is the embedded HAL crate, which is like common interface between libraries and all architectures. And are there plans of migrating the AVR HAL to the core embedded HAL?
Oh, actually, I saw something about redesigning those crates. Cannot really answer this question. I think I saw something about migrating to this common standard for HAL. Some parts are migrated. For instance, if I were to do delaying, and the delaying part is migrated to HAL, I would need to import this embedded HAL delay MS trait or whatever to actually get delay working. But I think like pins and stuff, so the rest of the low level is still like just some structs in this AVR HLL project. Okay, I see you are a bit off time, but I just have one more thing to show. Hopefully it won't take longer than 2 minutes, and it's a bit of a fun one. Okay, so before I was doing live coding, this time I have flashed something onto the microcontroller, and I'm going to attach to show it. And this is like buzzer, so this is a simplified version of a speaker. It doesn't require any of this. It doesn't require any of additional power. I can just power it through the pins. Again, somebody might yell at you that you need transistor or something. I say don't listen to them. I guess those were the pins. And to show you that I'm not streaming stuff from the computer, I'm going to plug it into power bank. I guess if you don't trust me, you don't trust this power bank either. So but to have the free text. And this will be some form of a simple contest because I have 4 songs in here. And as I said, I did not buy candies, so you cannot win anything beyond my great appreciation. Maybe it will just do it. Okay, so first one. Well, before I even start, does anybody have a guess what I might play? Okay, I don't know, not to have it too loud, maybe. Okay, I thought I had more notes there, but that was it. So obviously this was Rickroll. You cannot win anything, but I have 3 more songs. And they are not as simple, so I will be asking if you know, you can raise your hand. And I will not clap to you because this will kill the streamers, but you will win my appreciation as I said it. Okay. Any idea? Yeah, which song?
The model.
The model, yeah, that was fast. Nice, so. Okay. This is a bit more difficult, probably unfair to some people on the with us because it's entirely Polish song. But maybe my girlfriend didn't guess it because, and when I said it, she said it's badly composed. I mean, because I was just transcribing from the ear, so this might be off. But does anybody have a guess? Okay. Yeah, that's the one. That's Brodka, miał być ślub. Yeah, I guess. Okay, and that's the latest one. I think this will be very easy to guess, so this is mostly for fun and to finish. Oh. Okay, so I just have one more final slide before I finish. I won't be talking anymore because this is to leave you with a joke at the end. And I guess this would be a thank you. So if you got interested in AVR, then great, go buy all AVR stuff. If not, then well, rewatch the stream. You have to get interested in AVR if you haven't. And yeah, thank you.